We continue with our discussion on financial management under Unit 1, Introduction to Finance. In this particular video, we are going to discuss the concepts of compounding and annuities and perpetuities, which are specific kind of cash flows, and how they kind of impact decision making, what are the kind of various formulae that we need to learn, and what are the concepts that we'll need to learn. We'll also try a few problems along with this now, because this is now getting into a little bit quantitative aspects, and the idea being that because these formulae are used again and again, we should have a fair sense of how do we calculate these, both conceptually as well as using Excel. The first concept that comes to our mind is the concept of compounding. We have already seen the concept around compound interest. Compounding essentially means that you're earning interest on interest, right? So this is a scenario where you're earning interest on interest. So the concept stays like this, that a lot of the times the interest is paid on instruments at a frequency which is more than once a year. You can deposit 100 rupees in a bank and the payment could be at, let's say, a 12% interest, but it may not be annual. It may be semi-annual, it may be quarterly, it may be monthly, right? For example, a bank that offers monthly interest rates that can get compounded 12 times a year. The interest you get in the first month gets added, and then in the second month you have the entire amount on which you get the interest. In the third month you have this entire amount on which you get the interest, and so on and so forth. So what happens is you will know that effectively the final return will get increased, because now on every month's interest you are getting some more interest, right? However, remember that rather than, even if they are giving a monthly interest, rather than quoting the monthly rate, institutions like banks and other financial institutions quote the annual rate. This is known as the stated annual interest rate, or quoted interest rate, or just stated interest rate, right? When you are saying 12%, this 12% is in annual terms, right? Now, suppose a bank compounds interest on a monthly basis. What does that mean? Every month you take your stated interest, that is stated interest rate, and divide it by the number of periods that the interest will be paid for during the year. In this case, if it is being paid monthly, the number of periods is 12, which means every month you are being paid 1%. Correct? Now, if this was a simple interest component, every month you will make 1 plus 1 plus 1 plus 1, 12 times, that will give you 12, right? 12 times, that will give you 12. But this is, remember, compound interest. So how does compounding work? Suppose the bank gives 12% interest rate as its stated annual interest rate. It compounds monthly, which means every month you will generate interest. In the first month, your 100 gets 1. So that becomes 101. In the second month, 101 generates an income of 1.01, right? In the third month, you get an income of 1.02, 1.03, 1.04, and so on and so forth. Why is that? Is because in the second month, your interest is being calculated not on 100, but on 101. In the third month, the interest adds 100 plus 1 plus 101, and the third month interest is calculated on this entire amount. The fourth month interest is calculated on this entire amount. The fifth month interest is calculated on this entire amount. Now you note that by the end of the period, you have in the 6, 7, 8, 9, 10, 11, and 12th month 112.68 minus 100 divided by 100. That's your return, right? So that will be 12.68%. Correct? Now note that the bank had given a quoted interest rate of 12%, but effectively you made 12.68%, right? So while the quoted interest rate is 12%, effective interest rate for you is 12.68%, and that is the power of compounding, right? To understand this better, we can also look at another example and try and gauge this a little bit better. Before we go there, let's try and formally introduce a formula around this, right? So what it says is that effective interest rate is 12.68%, higher than the stated annual interest rate. Note that the interest is compounded more than once during the year, then effective interest rate will always be higher than the stated interest rate, because the stated interest rate does not take into account compounding. Compounding will always increase your inflow into your hands, the cash flows in your hands, right? So effectively, the interest rate that you get if the compounding frequency is more than once a year is going to be higher than the quoted or stated annual interest rate, right? Let's try and formally introduce this. What did we do? So what we did was effectively we introduced 100 rupees for a period of for 12 periods at 1%, right? Instead of our initial idea, which was 100 into 1 plus 12%, right? This is if the frequency is once. If the frequency is 12 times, that's what we did, right? Now let's try and get into a formal definition of this. So future value is present value into 1 plus R by M into M by N. What are these terms? Quoted annual interest rate is R, which in our example was 12%, right? Frequency is M times per year, which is 12 times per year in our example, and number of years is 1, right? Let's try and put in the formula. Let's look at this formula. Present value is 100 into 1 plus R is 12%. The numerator R here is 12%. That's 12% divided by M. M is the number of times you will compound it during the year, right? That's also 12, right? And then multiply M, which is 12, into the number of years you're looking at. That's the future value you're looking at. So, right, that's the formula we introduced, which was 100 into 1 plus 1% to the power 12. If you compound it 2 times during the year, the formula would become 100 into 1 plus 12% by 2 into 2 into 1, which is equal to 100 into 1 plus 6% raised to the power 2. If you're compounding it, that's like semi-annual compounding. If you have quarterly compounding, which is 4 times a year, right? By logical deduction, we will reach this. You can try this out, and you can get a handle on how the number works. Now, in the same token, the effective interest rate that you're saying is, how do you solve for the effective interest rate? So we said 100 into 1 plus R to the power 1, right? Whatever is the effective interest rate is equal to 100 into 1 plus R by M to the power M, correct? I can remove this, I can remove this, which gives me effective interest rate is equals to 1 plus R by M to the power M minus 1. In our first example, if you think about it, effective interest rate is 1 plus R is 12%, M is 12, 1 plus 1% raised to the power 12 minus 1. If you solve for this, this will be 12.68%. So effectively, you don't need to remember or memorize the formula. You just need to kind of conceptually try and solve this. And if you solve this conceptually, you'll automatically get to the results that you're looking for, right? As you keep increasing the compounding frequency from annual to semi-annual, 2 times a year, to quarterly, which is 4 times a year, to monthly, which is 12 times a year, to daily, which is 365 times a year, your effective interest rate will keep increasing because you are compounding more number of times, right? There is also a theoretical concept where assume that the interest compounds every instant, every second, every moment the interest is compounding. This is called as continuous compounding. So far, we were looking at discrete compounding instances. The intervals were discrete. We could define 1, 2, 4, 12, 365. Now we are saying we can't really define it because every moment it is happening. So the number of compounding periods are infinite. In this case, we give the compounding future value as present value into e raised to the power, the rate, whatever the rate is, right? Stated annual interest rate 12% multiplied by the number of years. So if we were looking at continuous compounding, that will be 100 into e raised to the power 12%. And that will tell you what is going to be the future value of this after 1 year, right? Now that's a theoretical concept because in reality, there are some instruments which kind of assume continuous compounding. But in reality, when we look at banking instruments or fixed deposits, etc., there this doesn't really apply. This is more like a theoretical concept as such. So we'll take this as and when it comes across. I just wanted to introduce it at this point of time, but not very important immediately. We will look at the importance of this when we reach there, right? So let's summarize what we have said. If we have an annual rate of interest of 10% on an investment of 10,000, we every year we'll get rupees 1,000 as an interest income, right? Effective rate of interest, however, is if the compounding frequency is more than once, right? So effectively, if let's say you have a compounding frequency of twice a year, right? If you have a compounding frequency of twice a year, then after 6 months, you will get what, 5%, which will be 500 on 10,000 rupees. And after 12 months, remember, you are going to get 5% on 10,500, right? Which will be 525. So net amount that you make is 1025 on 10,000, which means your effective interest rate becomes 10.25% with 6 monthly or semi-annual compounding, right? It might be interesting to look at this feature and this impact on the Excel file. So that's the Excel file. Let us assume that a bank gives 10% as its quoted annual interest rate. Calculate the effective interest rate if interest is compounded monthly, quarterly, or semi-annual. So let's look at monthly first. Monthly would mean 10% divided by 12, that's 0.8% every month. You will note that at the end of this entire period, we are looking at effectively 1104.71. If you actually look at this, that's going to be 10.47%, right? Effective interest rate. If you were doing it quarterly, that would be 10% divided by 4. So 2.5, 2.5, 2.5, 2.5 every quarter. You note that you end with a number of 10.38% of return. If you do it semi-annually, you're doing 5%, 5%, and you realize that you end with a return of 10.25% at the end of the period, right? What does that mean? If we summarize, effectively, what we are saying is that at a compounding frequency of annually, effective rate stays the same as the annual rate. Semi-annually, it becomes 10.25. Quarterly, it becomes 10.34. Monthly, it becomes 10.47. Daily, it becomes 10.52. We can actually calculate it as well. This should be 10.38, sorry. So there's a small error here. This should be 4 times a year, but yeah, so that gives us 10.38. And you will note that here we have put in the formula. So the formula says effective interest rate is your effective interest rate is 1 plus the annual rate divided by the number of periods raised to power the number of periods, raised to power the number of periods minus 1, right? So that's 10%. If I drag this down, we will get these formula, right? So 10%, which is 812 divided by 365 raised to power 365 minus 1 gives me the daily compounding number. You will note that as your compounding frequency increases, the effective interest rate also increases, right? So with an increase in the compounding frequency, there is an increase in the effective interest rate as well. That's the premise of compounding. and something that is going to be important when these rates are kind of stated, right? Let's move ahead and talk about specific kind of cash flows. The first specific kind of cash flow that we introduce is something called as an annuity. Now, an annuity is, as the name suggests, equal cash flows at regular intervals, typically an year, right? So you're going to get, let's say, 1,000 rupees every year at the end of every year. If you're going to get 1,000 rupees every year at the end of every year for the next 5 years, the cash flow structure will be something like this. At the end of the first year, you get 1,000. At the end of the second year, you get 1,000. Third year, you get 1,000. Fourth year, you get 1,000. Fifth year, you get, at the end of it, 1,000, right? Now, we want to try and find out what is going to be the value of all these cash flows if they are invested at a certain rate R at the end of 5 years, right? So that's the future value of all these investments. That's like if I invest 1,000 rupees after 1 year, 1,000 after 2, 1,000 after 3, 1,000 after 4, and 1,000 after 5, what will be my retirement value, right? Now, some of these concepts we have already seen in terms of our Excel curriculum, but let's try and re-attribute this, understand this. So effectively, my first cash flow is going to get invested for a period of, if you see, 4 years. So this 1,000 will get invested at a rate of R for the period of 4 years, then 1,000 at the rate of R for a period of 3 years, 1,000 1 plus R 2 years, 1,000 1 plus R 1 year, and 1,000. This is happening right at the end, so this does not get invested. The summation of these cash flows effectively is going to be my sum or future value of the annuity, correct? That is given by this formula, where C is the cash flow, R is the rate at which it is getting invested, and T is the time frame for which it is getting invested. So in our case, 1,000 multiplied by 1 plus, let's say R is 10%, argument's sake, raised to the power 5 minus 1 divided by 10%. We have 5 cash flows and we have 1,000 rupees. That is what the future value of the annuity should look like, right? That's the formula. Okay. Now, let's go ahead and also introduce what is the present value of an annuity. Let's say you are going to get this cash flow for the next 5 years, and there is another certificate that is available. There is another certificate that is available that you can buy today and get entitled to these cash flows. Remember, this is similar to what we have seen in our previous section. There is some instrument that gives you 1,000, 1,000, 1,000, 1,000, and 1,000 for 5 years after this year, and you want to find the present value of that. How much do you pay for this certificate? So how do you calculate that? The present value of this 1,000 is 1,000 divided by 1 plus R. The next one is 1,000 divided by 1 plus R square, 1,000 divided by 1 plus R cube, 1,000 divided by 1 plus R to the power 4, and the final one is 1,000 divided by 1 plus R to the power 5. The summation of these will give you the present value, correct? Now, note something careful. We have already seen that present value is equals to future value divided by 1 plus R to the power T, right? So in our future value formula, if you divide by 1 plus R to the power T, this is our future value formula. Open up the formula, that's C into 1 plus R to the power T by R minus C by R. Now divide this entire thing by 1 plus R to the power T to get the present value, right? The numerator was the future value. I divide by 1 plus R to the power T to get the present value. That's what we have learned already. So if you do that, this 1 plus R and 1 plus R will cancel each other, and you'll get a 1 plus R by T raised to the power T in the denominator here, which will transform your present value equation to something like this. Note carefully, this equation is nothing but dividing the future value equation by 1 plus R to the power T. So what you get is effectively C by R, where C is the cash flow value, 1 minus 1 by 1 plus r to the power t. That's the present value of an annuity. Where is the concept relevant? Let's say after retirement at the age of 60, someone is going to get a certain amount of cash flows. This is how you calculate the present value of that series of cash flows. How much should you pay for that certificate today in order to receive this money, right? That's the calculation that you're trying to do, right? In our earlier example, let's look at these two examples of our future value and present value in the Excel file. So this is what we had exactly kind of seen earlier. Our cash flows are, let's say, happening at this point of time. Let's assume the rate is 5%. Let's assume the rate of interest is 5%. So effectively, my first cash flow gets invested for 5 years, for 4 years, the second one for 3 years, then 2, then 1, and then 0 years. And the sum of this gives me 5526. Let's try and solve it two other ways. One of the ways is actually using the formula. A here is the annuity. A here is the annuity. That's 1000 multiplied by, bracket opens, and within bracket I do another bracket open and I say 1 plus 5% raised to the power 5 minus 1. Correct? That closes the bracket, and I'll need to put in a multiplication sign here, and at the end of it we need to divide it by 5%, right? And let's see what the answer is. As we press enter, we get 5526, which is what we had just seen, right? Similarly, if I divide this entire equation by 1 plus r to the power n or 1 plus r to the power t, that's going to give me the present value function. Now, if I'm going to get these after 5 years, the present value is calculated by each one discounted by a certain number of years. I can use the calculation as well, which is 1000 multiplied by, bracket opens, 1 minus, in fact, let's have 1 minus 1 divided by 1 plus 5% raised to the power 5, correct? And that's the first bracket closed, that's the second bracket closed, divided by 5%. I hope we have put in the brackets correctly. We get 4329, which is what we had calculated earlier, 4329, right? So exactly the same value. The same could also be used using the FV function, correct? So FV, future value, what is the rate? 5%, number of periods, 5, payment amount, 1000, and in this case minus 1000. There is no present value, and we are assuming a payment at the end of the year, so we leave type blank. What is it that we get? 5526. Similarly, we can use the function PV here, open brackets, rate is 5%, number of periods is 5, payment is minus 1000, and okay. And once again, we get the same value, which is 4329. So you can solve it multiple ways. You can directly use the function FV and PV in Excel. You can use the formula that we have just seen in order to arrive at the value. And you can individually try and solve each of these in Excel as well, and you'll still get the values as per your understanding, right? That's the power of Excel. That's how you calculate the value of an annuity. Let's do a quick question on this. Suppose you have taken a car loan and need to pay 1 lakh rupees every year end for the next 5 years, then what is the present value of all the payments that you have made, right? So what is the present value of all the payments that have been made is what is to be seen. So in our equation, remember the formula that was C by R, which is 1 lakh by 10% minus 1 lakh by 10% into 1 by 1 plus 10% to the power T, right? That's what we had seen. That's what we calculate. We take this value outside, which is the cash flow of 1 lakh, and 1 by 10% minus 1 by 10% into 1 by 1 plus 10% raised to the power 5. This colored part is known as the annuity factor. If we solve for this, we will get a value of 3.79, the present value will work to 3,79,000. Though you are paying 1 lakh every month, every year for the next 5 years, which means you have effectively paid 1,11115 lakhs. The present value of that is 3.79 lakh rupees, right? And that is the concept of present value of an annuity that would come across. We move ahead and we talk about an annuity which is going to continue till infinity. Such an annuity is called a perpetuity, right? Now, perpetuities are interesting components because it's being said that till infinity you're going to get the same cash flow, right? So if you have 100 rupees or 1000 rupees and you're going to get 10% on it till infinity, then each cash flow is going to be 100 bucks. And you'll keep getting 100, 100, 100 till infinity, right? How do you value the perpetuity? Work backwards. We said we started with the value of 1000 rupees invested at 10%. It's going to give me 100, 100, 100 each year. So if I take 100 each year and divide it by 10%, that gives me 1000. That is how you calculate the present value of an annuity, right? You take the cash flow divided by the discount rate that is there, divided by the rate of interest that is there, and you will get the present value of the annuity. So if you want to donate rupees 10,000 every year in perpetuity, then how much investment you have to do today? Discount rate is 10%. If you invest 1 lakh rupees, which is arrived by dividing 10,000 by 10%, as C by the rate, that's going to give you 1 lakh rupees. If you invest 1 lakh rupees into the bank account today and that gives you 10% every year, that 10% every year will keep giving you 10,000, 10,000, 10,000 every year, which you can donate to the cause, whatever cause you're looking to, right? So that's a simple calculation. Sometimes the perpetuity doesn't start immediately. Let's say you want to donate 10,000 every year in perpetuities, but after 3 years, then how much investment you have to make today, right? So now understand this: 0, 1, 2, 3. Here is when you want to start the perpetuity, correct? This is where you want to start the perpetuity. Now, if you do a value calculation of 10,000 by R, which is 10%, the 1 lakh rupee has to be invested at the end of the third year. If you invest 1 lakh rupees here in third year, then you're going to get the perpetuity for every year after that. So today you don't need to invest this. Today you need to invest 1 lakh divided by 1 plus R to the power 3. That's the present value of 1 lakh rupees today. So 1 lakh gets divided by 1 plus R to the power 3. That gives you the discount factor or the present value factor as this. If you invest 75,131 today, that in 3 years will become 1 lakh rupees, and that 1 lakh rupees after 3 years is going to give you 10,000 every year till perpetuity, right? That's how you solve questions on perpetuities, annuities, and compounding. That concludes this particular section. You will get a set of problems around this which you can try and solve. There will also be solutions around the problems. So just try and get your hands on this, and as much as you practice this, it would become easier to kind of comprehend. This is where this particular section ends. In our next section, under Unit 1, Introduction to Finance, we're going to discuss the concepts of net present value and internal rate of return.